All right, well, welcome everyone. We're gonna just jump right in here. We're very lucky to have PoNing Chen from UC Riverside. Today he's gonna talk to us about quasi-local approaches to angular momentum in general relativity. Please.
Hey, thanks Martin for the introduction. And so I will talk about is a quasi-local approach to angular momentum in general relativity. And so in particular, so I want to emphasize a particular problems about angular momentum at null infinity. So to answer what is the sort of angular momentum carried away by a gravitational wave or gravitational radiation. Now at null infinity, the main difficulty comes from the supertranslation ambiguity. So we will discuss how we use the series of quasilocal conserved quantities to resolve this difficulty. That's the sort of the title of a quasilocal approach to angular momentum in general relativity. Now, in the first half of the talk, I will talk about what is the difficulty that we're trying to resolve. So we'll start with the angular momentum in classical mechanics and special relativity to set the sort of expectation of what properties one should expect for angular momentum in general relativity. Then we will specifically look at null infinity, described using the bounded Sachs formalism in general relativity. And in that framework, describe what is the supertranslation ambiguities and how we use the quasi-local angular momentum to resolve that issue. So firstly, a very quick review of angular momentum in classical mechanics. Right, you have some particle moving with some position r and some mass m and velocity v. The angular momentum measured to some reference point is, well, m times r cross v. Now, because this everyone knows, what happens is if we do a coordinate change and translate the origin, how does the angular momentum change? And it's not difficult to see that it changes by, well, how much we translate our center across the linear momentum. Okay. Simple exercise. And this will be, well, this is what eventually we hope to achieve in general relativity. Now, how does angular momentum and other conserved quantity work in special relativity? Right, again, from the Nernst's principle, each continuous symmetry corresponds to a conserved quantities. Energy is corresponding to the time translation. Spatial translation give you the momentum, rotation, and boost give you the angular momentum and central mass or central mass integral. Specifically, you have a particle moving, then the energy, linear momentum, angular momentum, and central mass can be obtained by pairing the velocity with your isometry. Right? Again, in this framework, it's very easy to see that what happens when you do a coordinate transformation. You translate time by some constant, translate the position by some vectors, alpha 0 and alpha I. The energy and linear momentum remains the same. The angular momentum and central mass shift by, well, angular momentum shift by the same rule as before, the original one plus the cross product between the space that you shift, spatial coordinate that you shift cross the angular momentum, cross the linear momentum, and central mass have a similar change formula. These are easy to verify. Okay. Now, how do we handle this in general relativity? In particular, how do we, if we want to focus specifically on null infinity, how do we describe null infinity in general relativity? There are many possible approaches. In this talk, we will focus on the bounded coordinates mostly for sort of computational simplicity. In a later talk in this conference, Yekai Wang will talk about, well, in fact, this treatment is not limited to a boundary coordinate. In a later talk, Yekai Wang will talk about how we can achieve the same thing using double null foliations. And I suppose I forgot to mention, this talk will be based on joint work with Jordan Keller, Mu-Tao Wang, Yekai Wang, and Shing-Tung Yau. Okay, so in the boundary coordinate system, we assume at least near the infinity, we have the following coordinate for the space-time. This is, of course, modeled over the Minkowski space or even the structural space-time. U and V goes to 1. The induced metric HAB goes to the wrong metric on the S2. WA goes to 0. Of course, if you set WA to 0, HAB to wrong metric, U and V equals to 1, you get this metric in the Minkowski space. And so this is the ansatz for an asymptotically flat space-time. And the level set of U give you a null cone. You set U to be constant, the metric becomes degenerate, just R squared times HAB, DXA, DXB. And U is the retarded time, R is the luminosity distance from the black hole. Okay, so the null infinity corresponds to R equals to positive infinity, and on which U goes to positive and negative infinity correspond to the future time-like and space-like infinity. Okay. Now, this is a particularly nice coordinate to study sort of gravitational radiations because, well, the physics of gravitational field, they are encoded in the expansion of the above coefficients, and in particular in V, HAB, and WA. So we'll assume that one has a power series expansions of the following form. V is 1 minus 2n over R plus lower order terms. M is the mass aspect. In the structure, of course, you get M to be constant. HAB starting with the standard metric on S2, you have next order term is CAB over R, then lower order terms. WA, you start with 1 over R squared, and there is a angular momentum aspect and A embedded in the 1 over R cubed term. The advantage of this coordinate system is that the Einstein equation then reduced to a system of ODEs. So first on a level set, on a null cone U equals to constant, everything is determined by HAB as ODEs in R, except a few constant of integrations, particularly M and NA, mass aspect and angular momentum aspect, which are sort of free variables constant of integration that you can choose on a particular slice U equals to constant. Everything else, U, V, the rest of HAB and WA are determined by, the rest are determined by HAB. Now, once we start to evolve such data to a different level set of U, then again, the remaining Einstein equation reduced to ODEs in U. Okay? There is a sort of free source term. The derivative of CAB in U is something that one can choose freely, okay? Which is called a New's tensor. Every other thing, including those mass aspect and angular momentum aspect, which are free things that you can choose on a slice, the evolution are fixed by this New's tensor. For example, the derivative of the mass aspect satisfies the following: some combination of double divergence of the New's minus the norm square of the New's. And there's a similar formula for the du of NA, which I will omit here. Okay. So these are very convenient computationally. Of course, this only sort of solve the space, give you a portion of space-time near null infinity. whether or how you can fill in is a different matter that we will not touch today. Okay, so now we have this coordinate systems. What are the mass or energy, linear momentum, angular momentum of a slice u equals to constant? The energy and linear momentum, these are sort of well understood, and they depends on the mass aspect n of ux, right? The up to some normalizing constant, the energy is the integral of n, and the linear momentum is the integral of n against the coordinate functions x1, x2, x3. So the standard coordinate functions of S2 in R3. Okay. So not only, so maybe why this type of expressions for conserved quantities? Right. This sort of happens. This integral on x2 should be think of a x2 sitting at r equals to infinity. So you're sort of taking a now cone u equals to constant, you compute its total energy and total linear momentum by some integral at its boundary, which is at infinity. So again, I mean, the most intuitive way to define energy or other conserved quantity in some region is to integrate some sort of density over your region. However, this is not possible because of the equivalent principle in general relativity. So gravitational energy doesn't have a density. So you cannot compute this as a sort of integral over n. So instead, you define it as some integral over boundary of n. Right, so, right, for example, the ADM energy momentum for at spatial infinity take a completely different form, but still it's sort of a boundary integral on boundary of n. This is sort of what I want to emphasize here. Okay. Now, how does this energy or mass changes when we evolve our space-time by the Einstein equation? So on here, and for the previous formula, you don't necessarily have to have sort of a complete square plus from u equals to minus infinity to u equals to plus infinity. But for the discussion from here on, let's assume we have so square plus extend from u equals to minus infinity to u equals to plus infinity. Now it's simple to derive the change of boundary energy. Right? You integrate the mass aspect, and we differentiate the mass aspect functions. Right, the double divergence doesn't matter, so you're easy to see that derivative of the energy is -1/4 times the integral of n squared, which is negative. So in a sense, your energy is always decreasing. Also, from here, you can write down the total energy radiated away in this particular boundary coordinate systems, right? The E at positive infinity minus E at negative infinity. Well, you just integrate the derivative. Right? So you integrate n squared on x2 and then on u, so integrate n squared on square plus. And there's some constant in front, but again, so this gives you the energy radiated away, or at least in this particular boundary coordinate system. And of course, by this point, one should think about, well, in GR, there's no canonical coordinate systems. So what if one choose a different coordinate systems? But we'll come back to this question in a moment. Now, the angular momentum at null infinity, this is turned out to be much more subtle. There are different approaches and different distribution of null infinity, which leads to different definition. So there's Ashra-Hansen, Barnage-Torsat, Branson, Kusher-Jeski, Dauk-Manson, Drey-Stubel, Hawken-Perry, Strominger, Rizzi, and so on and so forth. And this is not a sort of complete list. But what we will take as sort of the classical definition of angular momentum and null infinity, we will use the Drey-Stubel definitions. So you take the rotation killing field, integrate against the following term, vector field, which the main term comes from the angular momentum aspect in the expansion of WA. Then there is a quadratic terms of the shear tensor CAB. Okay. Now, we mentioned before about this possible coordinate changes. So what is the symmetry group of square plus? This is the Bundy, Metzner, Sachs, BMS group. So this you have sort of an enhanced symmetry group rather than the usual Poincare group. You have a much larger BMS group. In fact, this is infinite dimensional now. And in general, this is not the enhancement of symmetry. Is not necessarily a bad thing. You get a lot more things you can use. Okay, but roughly speaking, these are coordinate transformations and null infinity, which keeps the Bundy-Sachs coordinate forms. Okay. So as we said before, well, there's no preferred coordinate in general relativity. So what if we use a different Bundy coordinate system to describe the same event, the same gravitational radiation? How does that changes, for example, the energy radiated away that we write down before, or in the question that we're going to study, does that change the angular momentum that is radiated away? But before that, what is this symmetry group? So in addition to the Poincare group, this now in addition have the following supertranslation. So this corresponds to on square plus a change of coordinate u bar equals to u plus a function f of x. And you can already see that square plus has the degenerate metric dx squared. So in fact, it doesn't matter how you cut. You can cut by u equals to constant, or you can cut by u equals to some fixed function f of x plus a constant. On the induced metric, you won't be able to tell the difference. You won't be able to know which, well, you don't have a reason to think that u equals to constant is better than u equals to a constant plus f of x. In fact, both sort of can be completed to a Bundy coordinate system with powers in R. So they are sort of equally good as Bundy coordinate systems, u and u bar. So for the later discussion, we will decompose the function f into harmonic mode, constant alpha 0, then the -2 eigenfunctions, combination of xi, and then the mode greater than or equals to 2. The constant mode corresponds to a time translation. And the -2 mode, alpha I, corresponds to a spatial translation. Okay, now so for a translation, for a super translation u equals to u bar, on one side I have a Bundy coordinate u r x a. After translations, I have another Bundy coordinate u bar r bar x a. How does this fundamental data, the news, the shear, the mass aspect, how do they transform? And also the angular momentum aspect, how do they transform in such a coordinate change? So here we write down some of this. The news tensor so transform the simplest. The news tensor is just the news tensor at evaluate at the different point. For the shear tensor, you already see the main term is the shear tensor at u bar plus f, but you also have this traces Hessian of f appear in C bar. The mass aspect and bar in the u bar coordinate system. Again, the leading term, you have the mass aspect computed at u bar plus f. And you have a bunch of terms coming from the mu's. Okay. Now, however, from this, one can check the following, that the energy radiated away that we write down before in the u coordinate system is the same as the energy radiated away in the u bar coordinate system. And this is in the u coordinate system, right? I have this integral of n. In the u bar coordinate system, I have the same thing, but using the nu's in the new coordinate system u bar. Now this plus any sort of reasonable decay rate of the nu's tensor to guarantee that I can use the Frobenius series will guarantee that these two are going to be the same. Okay. So in other words, there's no sort of ambiguity to the energy radiated away. It doesn't matter which coordinate system that I use. Okay. The energy radiated away is well defined. Okay. Now, the next question is, well, how about angular momentum? There has been sort of a worry that this won't be the case for angular momentum. Penrose wrote down that they feel that the sort of concept, the angular momentum gets shifted by this supertranslation, that it is hard to see how one can rigorously discuss such questions as the angular momentum carried away by gravitational radiation. Or in other words, suppose you have two different coordinate systems, u bar and u. One worries that the energy radiated away you compute in the u coordinate system delta j is not the same as the one the delta jf that you computed in the u bar coordinate system. So we will refer to this difference as the supertranslation ambiguity of the angular momentum. So first thing is, well, what exactly is this supertranslation ambiguity? So you worry that there might be an ambiguity, but can we sort of quantize it? What exactly is this ambiguity? So here is the recent result with Jordan Keller, Mu-Tao Wang, Wang, and Shing-Tung Yau. So assuming that the nu's tensor decay as follows, which is u to the power -1 minus epsilon. And suppose I have two boundary coordinate systems u and u bar, which are related by a supertranslation f. Then the change of angular momentum observed in the two coordinate system, the difference is given by the following integral. So you take the mass aspect, take the limit at plus and negative infinity, then you apply the rotation field to it, multiply by f, then integrate on your surface. Okay, so this is then the supertranslation ambiguity. Okay, so in particular, as long as YA applies to n plus minus n minus half L greater than equals to mode, then the total flux, the total change of the Drake-Struble angular momentum can assume any value after applying a sort of pure supertranslation. So in other words, you indeed have an ambiguity as long as this function has L greater than or equals to 2 mod. Now, how does the proof work? Well, it's similar in spirit to the previous argument we used to show that the energy radiated way is supertranslation invariant. So we start by computing the derivative of the Drake-Struble angular momentum, which can be written as the following integral. Then the total change will be the integral of this from -infinity to +infinity. Okay. Now this is what one can compute in a u coordinate. In the u bar coordinate, one will have the same expression, except both the shear and the nus in this last line are replaced by c bar and n bar in the other coordinate systems. Now one can write down, go back to here, how does the n and n bar, c and c bar are related. The decay rate, again, guarantee us that we can apply the Fubini theorems. Okay. And there's some more sort of integration by parts, both in the space on X2 and on U that you have to perform. But from there, one can, and also use the Einstein equation in the boundary coordinate system, one can derive that sort of integrate completely in U, so that the final result is just the difference of quantum mass aspect at plus and negative infinity integrated on an S2. Okay. So far we identified the supertranslation ambiguity of the classical angular momentum. Now, how do we use a quasilocal approach to find a new angular momentum which is free from such ambiguity? Okay. So we will use a sort of the quasilocal approach to define conserved quantity based on the series of quasilocal mass of Wang and Yau. So the main motivation behind this definition of quasilocal mass, and also our later definition of other sort of quasilocal conserved quantity, is that the Minkowski space, which is completely flat, should contain no gravitational energy or any other conserved quantities. So in other words, a well-defined quasilocal conserved quantity should vanish for any surfaces in the Minkowski space. Okay. So this motivates the use of Minkowski space as some sort of reference space to compute difference of surface Hamiltonian or whatever your expressions for your energy or angular momentums. Okay. So take any two surface, space I two surface sigma in a given space time. So we first extract the sort of physical data, the induced matrix sigma, the mean curvature vector H, and the connection one form of the normal bundle of sigma in the mean curvature gauge alpha H. Now we want to embed the surface isometrically into R31. There is actually a degree of freedom that one can choose. So fix a coordinate system T, X, Y, Z in the Minkowski space. We can prescribe the time component freely we prescribe x0 equals to tau. Tau can be any function that you choose. Then in order to isometrically embed, you solve the following equation on x1, x2, x3. So this dAxi, dBxi, sum over 1 to 3 equals to sigma AB, partial A x0, partial B x0. So this would isometrically embed the metric on the right-hand side into R3, this matrix. If you solve this equation, then x1, x2, x3 isometrically embed the metric on the right-hand side into R3. And the matrix sigma AB, the isometric embedding into R31 is recovered as a graph x0 over that embedding. And of course, by the result of Nuremberg on the solution of Nuremberg to the well problems, as long as the right-hand side has positive Gauss curvature, there is a unique solution x1, x2, x3 up to translation and rotation of R3, which in particular doesn't change the sort of geometric data's mean curvature and the connection form. Okay. So the isometric embedding consists of x0, x1, x2, x3, give us a configuration of the surface sigma in R31 as a reference surface. And on the reference surface, we can extract the same type of data, the mean curvature and the connection in the mean curvature gauge. Okay. Then we introduce the following sort of two quantities. It's sort of a quasi-local mass density, which is a weighted difference of the mean curvature. You see the H0 is here and here and here, weighted by the center here and here, and also this denominator. And a sort of quasi-local momentum aspect, which the main term coming from the difference between the connection form, but then again corrected by some expression of tau. Okay, now this embedding provides sort of a canonical gauge where one can evaluate the surface Hamiltonian written down by Brown-York and also Hawking-Horowitz. So, and compute the difference of the surface Hamiltonian in the physical space and the reference space. One can write down the energy of the surface corresponding to this isometric embedding. And in terms of rho and J, this is rather straightforward. The integral of rho minus J, you apply gradient tau to it. And really gradient tau is the, minus gradient tau is the tangential part of the time translation ddt. And of course, when tau equals to 0, this will reduce to the Liu-Yau quasi-local mass, where you embed into R3 and pull back your gauge, canonical gauge accordingly. Of course, this assign an energy for each embedding. When you prove that the positivity of this quasi-local energy and define the quasi-local mass as the minimum of the quasi-local energy among all isometric embeddings. Okay. Now, to understand this minimizing process, of course, one asks, well, what is the Euler-Lagrange equation? And in fact, the Euler-Lagrange equation to minimize the quasi-local energy is nothing but the momentum, quasi-local momentum JA is divergence free. Well, this is a bit surprising because one have to, I mean, rho and JA both depend on tau, and in a sort of rather global manner. If you change a different tau, your isometric embedding is going to change. Your H0 will change and also change globally. Even if you change tau at around a point, then on the whole sphere, your rho is going to change. Similarly, your J is going to change. But this result would almost look as if, well, in this expression, I vary taus and rho and J are independent of tau, so the critical point equation is divergence of J equals to 0. It's come out from a lot of cancellations, but the Euler-Lagrange equation turned out to be simply divergence of J equals to 0. So now, before an isometric embedding, you have a freedom that you can choose, which is this tau, to solve the equation 1. So now you couple this equation 2 together with it, you get 4 equations on your 4 unknowns x0, x1, x2, and x3. And this at least the number of equations and unknown are now matched, so you have a better chance to feel that, well, the combined system will have better properties, for example, unique solutions. And indeed, for surfaces near the null infinity, the system of equation 1 and 2 indeed has a unique solution. This is studied in our joint work to evaluate the limit of Wang Yau quasilocal mass at null infinity, and which we show that it recovers the bounding mass. Okay, and there's also additional work as to, well, even if 1 is not close to infinity, well, what are the possible other conditions can guarantee the existence and uniqueness of solutions to the system? We will not discuss it here. But at least sort of near null infinity, which is sort of what we are interested in this talk, that this system has a unique solutions. So now from here, assuming I'm in a situation where the system have a unique solution for minimizing the quasilocal mass, how do I define the, for example, angular momentum and central mass? Right now I can transplant a Killing field, or the Killing field of R3 can either be rotation or boost through this unique solution back to my surface. I can define the following corresponding conserved quantities to be a following. Sorry, I'm actually missing a image from here. So of course, if I take y to be t0, this will recover the quasilocal energy that we wrote down before. Right, t0 dot t0 is -1. We mentioned before that the tangential part of t0 is minus gradient tau. Okay. Now, in particular, if I choose a rotation perpendicular to t0, then the quasilocal angular momentum is simply the following. So now the first term goes away. So the quasilocal angular momentum is simply I find the tangential part to the isometric embedding in R31, evaluate that vector field to my J, and integrate on my surface. So even at the quasilocal level, this quasilocal angular momentum satisfies many nice invariant properties. For example, for surfaces in the Minkowski space of the, well, rho and J will be 0 since you're taking the difference of something to itself. So all the conserved quantities will be 0. So in particular, well, since everything is 0, there's no supertranslation ambiguity. In fact, you don't even need a flux. The angular momentum for any surface is 0, so there's no ambiguity at all in change of coordinates. Okay. And also, if you translate, I mean, there's a freedom of translation of the isometric embeddings. If you translate that, then it change your angular momentum and center mass integral as what you would expect it from the special relativity picture. Okay? So this would suggest that if we use the limit of then at infinity of asymptotic space-time, then we should get total angular momentum as well as total center of mass that has good invariant properties. And this is in fact what we will see, that is indeed at the non-infinity, this will resolve the supertranslation ambiguity. So the limit of this quasilocal angular momentum at the non-infinity using the boundary coordinate is computed by Jordan Keller, Wang, and Yau. And to express the result, we need to decompose CAB into the sort of this using its potential. So CAB is symmetric traceless, so you have 2 dimension, and this 2 dimension sort of comes from a traceless Hessian and a sort of part which is dual to that, C and C bar. Okay. So indeed, after a fairly long computation, it turns out that the limit of the quasilocal angular momentum had just one single correction term to the Drake-Struble definition, which is C times gradient of n, and then you contract that with your rotation Killing field. So again, see, because it's the potential, so it's a sort of non-local term. If you change CAB at a point, you would change the potential everywhere on X2. Okay? And this is the first time that such a non-local term show up in a definition of angular momentum at non-infinity. There are many different definitions prior to this, but none of them has this type of non-local term. And sort of the main result of this talk is, well, after this correction term, which comes from the quasilocal theory, we get a new angular momentum, which is supertranslation invariant. In other words, if I do a coordinate change like before, then the change of the flux is what one would expect from the special relativity angular momentum. In particular, if I do a supertranslation, then this difference of flux, first of all, it doesn't depend on this part at all. The pure supertranslation part doesn't affect the change in the total flux. Neither does this part, which is time translation. The space translation does affect the result, but in a sort of way that, well, what you expect when you do a spatial translation, your angular momentum would change by the cross product between this vector that you translate cross the linear momentum. Now, because we're in a radiated space-time, the before and after linear momentum would change by some delta p. So the change in delta j is precisely alpha I cross with this delta p. And well, so in other words, delta j is invariant under pure supertranslation, and the transformation rule is the same as the sort of special relativistic angular momentum. And the proof is rather straightforward. I mean, at plus and negative infinity, how does the potential transform under a supertranslation? Right. So let's go back to this. Right. This is how the shear would transform. So you see that you add a potential term, which is exactly here. At plus and negative infinity, you can think of CAB at plus infinity is really a constant, which doesn't depend on your use. So really, when you do a supertranslation, the potential at plus and minus infinity just changes by f. And that term precisely would offset this supertranslation ambiguity in your standard definition. But from here, it's quite a straightforward argument to see that this is indeed the new angular momentum we define is supertranslation invariant. Okay. Indeed, also because we also have the quasilocal central mass, by taking its limit, one can also define the total central mass at null infinity. And this forms a sort of, again, all of this vanishes for any boundary point system of the Minkowski space when there is no gravity. So in the curved space-time, this recover what you expect. And in general, the total flux is supertranslation invariant. And sort of under the space and time translation, they behave according to the basic physical laws that you expect for ordinary transformation. Okay. I will stop my talk here. Thank you.